Hi, today we're going to talk about radius and interval of convergence. Now in part 1 we're going to spend some more time with how to find the radius of convergence. Now remember, the whole purpose of any series is to find out if that series converges or diverges for the most part, and that's important for us. Now when we first started talking about convergence and divergence, we started with a simple series. Now, if I have a series right here, and I'm letting n go from 1 to infinity, let's go from 0, we'll talk about why that is later on. If we expand this, we would get a sub 0 plus a sub 1 plus a sub 3, and so on and so forth, an infinite number of terms. Now, that's a series. Now, a Taylor series, or which generates a Taylor polynomial, is exactly the same thing. We have this a sub n, but we're going to multiply it by our polynomial part from our Taylor series, x minus c to the n. Now you might be thinking, but Mr. Wernow, isn't the Taylor series written as the nth derivative at c over n factorial times x minus c to the n? It is, but this a sub n right here, that's just our sequence from earlier. So this is just our sequence right here. In other words, from yesterday, that's our a sub n. That's our sequence, which is right here. We just make it simpler. And if I were to expand this, we would get a sub 1, x minus c to the first, 0 in this case, plus a sub 1, x minus c to the first, plus a sub 2, x minus c squared, and so on and so forth. Now, when we talked about sequences, it's easy to determine if a sequence converges or diverges if we write as a series. That's just all those tests that we learned. But the problem is when we add in this polynomial part, this x minus c. The question that we're going to say today is, well, are there values that can prevent values for x that will cause this series to converge or diverge? And that's what we're going to answer today. So today the whole goal is to make a function converge. So the question is, how do we do this? The question is, how do we determine if a function or a series converges? Well, basically what we do is we're going to use one of our tests. Now the easiest test to use for convergence or divergence is going to be the ratio test. Because remember what the ratio test says, if I take the limit as n goes to infinity of a sub n plus 1 over a sub n, and if that's less than 1, the series will converge. And that's what we want. We want the series to converge. So what we're going to do is we're going to take our series and we're going to apply the ratio test to it. And it's not that bad in this case. We get the limit as n goes to infinity of 3x to the n plus 1 divided by 3x to the n. And if I simplify this, we get the limit as n goes to infinity of just 3x. And for this to converge, this whole limit has to be less than 1. And that's the whole thing. If the ratio is less than 1, then the series must converge. So I can just solve this. Now notice it says as n goes to infinity, but there's no n. So I could also rewrite this as just the absolute value of 3x times the limit as n goes to infinity of just the number 1. We'll take a look at a more challenging example later on. And this has to be less than 1. Well, knowing what we know about limits, as n goes to infinity, since there's no n, this just always stays 1. So what we're left with is the absolute value of 3x being less than 1. Now, this part right here tells me my radius of convergence. So, and what this is telling me is that my radius here is 1. That the radius of convergence is 1 unit. So this will tell me as long as this absolute value, as long as the absolute value of 3 times x is less than 1, this series will always converge. And this is what it says. If the absolute value of 3x is less than 1, our series will converge. That's called the radius of convergence. Now we can use this to get what we call the interval, which we'll talk about in another part, okay? But let's take a look at another example at trying to find the radius of convergence here. So let's take a look at example number 2 here. Let's take a look at another one. Let's say we have the series n equals 0 to infinity, negative 1 to the n, x to the n over 5 to the n. And I just want to find the radius of convergence on this one. Well, to get the radius, my rule says use the ratio test, because the ratio test will guarantee something will converge. Because kind of think of it like this. If I got rid of that x to the n, we know by the alternating series test that this will converge. But what if x were something like 5? Like, what if x was 5? I would have 5 to the n over 5 to the n. And I would just be adding negative 1 the entire time. And therefore, this would diverge. So the problem is there are values for x that can prevent this from converging. So we have to find out, well, what values of x will allow it to converge. So we use the ratio test, because the ratio test lets us know, guarantees something will converge if that ratio is less than 1. Now, if you notice, I'm going to do kind of a shortcut. Here's my original one. I will divide it by the, here's my n plus 1. I'm going to divide it by the original, so I'm just going to multiply it by the reciprocal. So 5 to the n over negative 1 to the n, x to the n. Remember, this is a sub n plus 1 over a sub n. I just multiplied by the reciprocal, a little bit short step there. This must be less than 1 still. And all I'm going to do is I'm going to solve this. So I take the limit as n goes to infinity. I'm going to be left with 1 negative 1. And as far as the x's go, I'm left with 1x on top. On bottom, I get 5. And this is less than 1. So what this is saying is that this series will converge if this limit is less than 1. So what I'm going to do, and again, if you notice, no n's. So what I can do is I can kind of factor some things out here. I can take out the negative 1 and I get the absolute value of x over 5 times the limit as n goes to infinity times 1 of 1 is less than 1. Well, we know from experience that's just 1. So we get the absolute value of x. Now I'm going to put the 5 on bottom here. It's less than 1. So now this says as long as this is the absolute value of x over 5 is less than 1, this series will always converge. So to get the radius, I'm just going to multiply both sides by 5. Because remember, from algebra, so it's less than 5. We'll talk about that in just a second here. So therefore, my radius of convergence is 5. And it's easy to kind of tell why we call it a radius, because in algebra 2, we said that absolute value is a distance. The distance from some number is less than 5. And anything less than 5, anything in that distance less than 5, it will converge. If we think of it in terms like a number line, let's say 0 here is my center. If I go out 5 units, I'm at 5. If I go back 5 units, we're at negative 5. So it's kind of saying anything between negative 5 and 5, this series will converge. Now, we do have to check the endpoint, but we're going to talk about that in another video. So let's take a look at one last example here, just to find the radius of convergence. A little tougher one here, number 3. Let's try this one. N equals 0 to infinity, 2n factorial, x to the 2n over n factorial. In other words, ouch. But if I apply my rule, n2 goes to infinity, this becomes, now this is 2n plus 1, right? So that just becomes 2n plus 2 factorial. Same thing here, x to the 2n plus 2 over n plus 1 factorial. Now, I am going to multiply that by the reciprocal of the original one. That's to get my ratio here. N factorial over 2n factorial, x to the 2n. This has to be less than 1. For this to converge, this value has to be less than 1. Now, what you're going to notice, we're going to be left with some n's here. So we take the limit as n goes to infinity I can simplify, because remember this is just 2n plus 2 times 2n plus 1 times 2n factorial. So those just cancel out. Same thing down here. This is just n plus 1 times n factorial. So those will cancel. And what I'm left with, on top, I get this 2n plus 2 times 2n plus 1 over n plus 1. But I'm not done yet, because take a look here. I'm still going to be left with an x. If I subtract those power, we're left with an x squared on top, less than 1. Remember that I just subtracted those. Now, remember, I'm only interested in the n, so anything that's not have an n in it can be taken out. So I'm going to be left with the absolute value of x squared times the limit as n goes to infinity of 2n plus 2 times 2n plus 1 over n plus 1. This has to be less than 1. And we run into a slight problem right here, and that's this right here. This, if I let n go to infinity, this whole term goes to infinity. So here's what it's saying. We're taking x squared, the absolute value of x squared, times infinity. We're going to see if that's less than 1. But here's the problem. This goes infinitely large, and that is not less than 1. So that fails. So the ratio test here fails. But what does it tell us? This tells us that this series will always diverge, except in one case. So therefore, we say this series will always diverge, except, and here's the kicker, when our radius is 0, except when the radius is 0. So I'm just going to set this absolute value of x squared equal to 0, so x equals 0. So what this says, if x is 0, this series will converge. Because think about it, if I let this be 0, I'm just adding a whole bunch of zeros. 0 plus 0 plus 0 plus 0. So it does have a radius, and it's 0. Alright, if you go to part 2, we're going to take a look at what we call interval of convergence. Okay? And that's kind of a bigger topic for us. Okay? So go into part 2 if you need to. Okay? Bye-bye.